All right, so welcome to my presentation, Blockchain Technology by me, of course. All right, go. Oh, so what is blockchain technology? So blockchain is a decentralized digital ledger that securely stores across a network of computers in a way that is transparent, immutable, and resistant to tampering. Each block contains data, and blocks are linked in a chronological chain. So a ledger, just to break it down a little more, is the recording of financial transactions. So every transaction in this ledger is authorized by digital signature of the owner, which authenticates the transaction and safeguards it from tampering. So the data can be seen, can't be corrupted. So here's some history. Gotta start off somewhere. So here's an excerpt from a brief history of blockchain technology that everyone should read. So a generation before Nakamoto's white paper, a University of California at Berkeley doctoral candidate named David Chaum outlined the blockchain database in his dissertation, Computer Systems Established, Maintained, and Trusted by Mentally Suspicious Groups. That was in 1982, 27 years before Bitcoin. So another quote from there says, in 2008, the history of blockchain technology got interesting when a related research paper appeared in online discussion forums. The paper was titled Bitcoin, a peer-to-peer electronic cash system, and it was attributed to Satoshi Nakamoto. And then lastly, it says the first modern blockchain was launched in January '09 along with the associated cryptocurrency Bitcoin. So it was started in 1982, and then by '08 we saw maybe the first modern version of it. So here are key components of the blockchain according to components of blockchain network. So nodes, which are computers that play a role in blockchain by creating a copy of it. Transactions, fundamental units of data in the blockchain representing the transfer of value or information. So a transaction is created, verified by nodes, and then recorded on the blockchain. So algorithms that allow the network to agree on the validity of a transaction and maintain a consistent state of the ledger are consensus mechanisms. So this includes proof of work, so POW, proof of stake, POS, and then delegated proof of stake, DPoS. So once again, from the same source, he kind of breaks it down, try to explain these consensus mechanisms. So proof of work requires participants to solve intricate mathematical problems in order to verify transactions. Proof of stake, validators are chosen based on the number of coins they hold and are willing to stake as collateral. And then delegated proof of stake says that participants vote for a small number of delegates to validate transactions on their behalf. We're going to revisit these mechanisms later, and you're going to see why. So how does blockchain technology work? Well, all those key components that I just stated are involved in the working of blockchain technology. To restate, each block contains stored data as well as its own alpha-numeric code called a hash. These cryptographically generated codes can be thought of as a digital fingerprint. They play a role in linking blocks together as new blocks are generated from the previous block's hash code, thus creating a chronological sequence as well as tamper-proofing. Any manipulation to these codes outputs an entirely different string of gibberish, making it easy for participants to spot and reject misfit blocks. Blockchain distribute control across a peer-to-peer network made up of nodes. They are in constant communication with one another, keeping the digital ledger up to date. So when a transaction is taking place among two peers, all nodes take part in validating the transaction using consensus mechanisms. These built-in protocols keep all in-network nodes in agreement on a single data set. No blocks can be added to the blockchain until it is verified and has reached consensus. So, blockchain has problems? Yep, I asked the same question. So, here's some of the problems. Scalability. So, saying that as the number of users, transactions, and applications increases, the ability of blockchain networks to process and validate them in a timely way becomes strained. Energy consumption. The process of validating transactions on a blockchain network requires a lot of computing power, which in turn requires a lot of energy. Security. There have been many instances of security breaches and hacking attacks on blockchain networks, and these problems can result in monetary losses or money losses and damage to the integrity of the network. Complexity. Tech challenges may hinder the widespread adoption of blockchain technology, and discourage potential users and developers from engaging with it. Blockchain's complexity can also lead to errors and inefficiencies in implementation. So here's some of the approaches that I found online. So complexity, efforts to address this issue include the development of user-friendly interfaces, streamlined onboarding processes, and educational resources that simplify the complexities of blockchain. Security, formal verification of smart contracts to help identify potential vulnerabilities and using multi-signature wallets for storing and managing digital assets. Energy consumption, alternative consistent mechanisms. So like I said before, I told you guys to, we're going to come back to that. So here we are. So let's start over. Energy consumption, alternative consistent mechanisms such as POS or proof of stake or delegated proof of stake, which consumes significantly less energy. Scalability, scaling systems for creating off-chain channels that allow for faster and more cost-effective transactions. So I believe one day at a time that these solutions are helping solve these problems because every day we see the increase of blockchain technology and people promote it and advertise it everywhere. Everybody's joining in and having their relatively positive results. So I believe that is working. So here's what I suggest, my solutions. So I think for scalability, we should create specialized, flexible blockchains for different industries, which can scale automatically based on need. Energy consumption, we can connect blockchain to smart energy grids so miners can use renewable energy when available, cut down on energy from non-renewable resources. Complexity, build blockchains that can automatically adjust and improve themselves based on usage patterns. Security, use blockchain-based digital IDs to secure personal information and reduce the risk of data breaches. So are there other things to learn in blockchain? So are there other areas and avenues we can research on? Yes. So the avenues such as healthcare, voting systems, real estate, and education. So blockchain technology has the potential to transform healthcare, placing the patient at the center of the healthcare ecosystem and increasing the security, privacy, and interoperability of health data. This technology can provide a new model for by health information exchanges by making electronic medical records more efficient, disintermediated, and secure. So that's a quote that explains how blockchain technology can help in the healthcare field. So for voting systems, we could research, we can examine the use of blockchain for secure, transparent voting in elections, eliminating fraud and increasing trust in the voting process. For real estate, you can study how blockchain can streamline property transactions, reduce fraud, and enhance transparency in real estate deals. For education, we can investigate how blockchain can be used for credentialing, academic records, and online course certification. So here's my works cited page. So I hope you guys enjoy my presentation and hope you guys have a great winter break.